Hi, everybody. As the music fades out here, welcome back to Chem 140. We are in week 5, which means two things. One, you're halfway done. Hooray! And that makes sense, because there's 16 units, and we might actually finish Unit 8 today, because Unit 8 is, here's the periodic table, and it's like 2 slides. The other thing, not as exciting, but still important, there's an exam coming up, as you can see by the little indicator that is currently blinking on the screen right now. It's in red because it's important. Yeah, you have an exam on Monday. What's an exam for this class? Basically, it's like I took all of your quizzes in terms of, like, length and content and whatever, and I stapled them all together. Like, you know, if we had paper and we're actually in class. That's more or less what an exam is like. Online, it's a little bit different than that, but it's more or less the same idea. You're going to be doing questions pretty similar to the stuff that you've already been doing. Like, I'm not going to throw a ton of curveballs at you after I've tested you on what I want you to know, because that's kind of the point. I'm testing you on what I want you to know. And so you're going to see different questions. There is the possibility that you'll see the same questions or similar questions, because again, it's up to the system, whatever problems you get. But I throw more problems in there. And you take the exam. You get an hour and 15 minutes of base time to do it. It's worth 75 points. The problem to point density is a little bit, I'm not really sure whether to say it's higher or lower. The problems that you will get will be worth more points. So it's more important that you don't make mistakes, because on a 3-point problem, you'll lose 3 points for getting it wrong instead of 2. But obviously, I'm not going to make one problem worth 10 points all or nothing. Like, I can't really go much further than that. But most of the exam will be questions worth 2 or 3 points. There will be multiple choice questions thrown in there, true or false questions, check all the things questions. You should have seen all of the different types by now, hopefully. So that nothing really comes as a surprise when it's like, oh, I have to be able to click on this thing. How do you prepare for the exam? I have a real simple answer for that, and that is to prepare for the exam in the same way that you've been preparing for the quizzes and anything in this class. Study, 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 study. Between now and Monday, when you take the exam, you should budget 20 or so hours to prepare. And you should have been doing 20 hours per week up till this point, I would hope, since we talked about that early on in the quarter. That includes lecture time, of course. But you do have to put in the hours to become good at this. If you're only putting in like 20 or 30 minutes a day... Oops, we'll hit show on that. If you're only putting in 20 or 30 minutes a day, it's going to feel like you know what's going on, and then you're going to get to the actual test and be like, crap, I don't know what's going on. Like, you don't learn how to become an Olympic figure skater by watching somebody on the internet run around on the ice and make it look good. In the same way that you don't become an expert at chemistry by watching me do 3 problems on a topic. Like, you had to do a lot of these problems. The reason that I'm so confident at doing this stuff is because I've literally put in 10, 15 years in just doing these types of things. And I could do this with my eyes closed. I could do it with my hands behind my back. I could do it while hanging upside down, by my feet, swaying back and forth over a cliff. I could do dimensional analysis. Like, it's super easy for me. But in order for you to get to that point, you just got to keep doing the work. And there's going to be quite a bit of dimensional analysis, because that's more or less the only math that we've done so far, with the exception of what we're going to do today, which is just addition and multiplication again. Is there a specific time when you need to take the exam? There is not. So a lot of other instructors, what they will do is, I don't know if I actually put the slideshow. Did I capture the slideshow? I did, okay. Let me get the chat on the screen here for the people who are watching this video in the future. What I do for exams is I give you 24 hours to do it, and you still get 2 attempts. You just need to do both attempts before the deadline. I can't extend the deadline after 11:59. So what will happen is that at 11:59 p.m. on Monday, the exam will automatically close and you won't be able to take it. If you need special arrangements from me, like, oh, can I please take the exam one day earlier, one day later due to XYZ reason that you would then tell me, that is almost always okay. I can't move it too much further than that because then the integrity of the exam could be compromised. But if like you're working on Monday and you have all of Sunday free, I'm happy to do that. I just need to make sure that I know that by at least Saturday, so I know, oh, I got to get the exam done for so-and-so student. But you get all day. I know other instructors are like, no, you must be present at these 2 hours. And I'm like, no, that's ridiculous because it's online. And I know other classes might have you doing class on Monday. So you take it before or after, I don't care. Whenever you want. And if something comes up that prohibits you from taking the exam, like, please let me know. The sooner you let me know, the better. Don't miss the exam. If you miss an exam in this class, I can't give you a passing grade. You have to at least attempt it, even if your score is 0. If it's blank, I basically have to give you a V. All right, other questions about what's coming up? Excuse me. I'm just going to sit here and drink my water. My water that I have put frozen grapes into because they are tasty ice cubes. Mostly because I remembered to buy frozen grapes this time. My cord is all tangled up here. What am I doing? There we go. Okay. Oops, wrong button. Yeah, I have a lot of that too. I gotta turn this pad of paper sideways. And, all right. So what we're going to do today, if you haven't already, go ahead and grab a periodic table. Go to ptable.com and just have that open in a tab nearby. We're going to calculate atomic mass, which is the number that is written at the bottom of each box. We're going to talk about what that means and how to calculate it to the number of sig figs that are on the table or some other number of sig figs based on whatever values that I go obtain from the internet, and also generally just how to look this stuff up. All right, so first thing we need to do is talk about what isotopes are. Now, on Thursday's lecture, we identified an atom by the number of protons it had. So this number right here was its identity. So the questions in the exam should be very similar to the quiz we've taken so far. Or we'll have more than on the quizzes. There will be more questions of different types. Because if I gave you all of the quiz questions, just like, again, one, you've already seen them all, so that wouldn't be much of a second assessment. And two, I wouldn't actually have enough for 75 points. So I will add extra questions into the banks and scramble them up. And then I just pull from those banks and say, okay, I want to give 25 questions. Like, I'm just picking a number here. I want to give 25 questions to the students, and here's what I want these points to be. So, like, this is a 2-point question, this is a 3-point question, this is a 2-point, and whatever. And have it auto-assign that. So you're going to get all different types of problems. If you compare your exam to somebody else's, it will be very different. But the content will be, on average, more or less the same. So try not to compare exams directly because it's not going to really be a great use of your time. Especially if it's like 10 p.m. at night. Like, just take the exam. And I can't stress this enough. Like, I have all these hurdles in place. Like, you can't go back on problems. You only get one problem at a time. All the choices are scrambled. The order is scrambled, etc. Like, the whole reason that all of these things are there is because I want you to just know how to do the problems and not rely on anybody else. That is the simplest way to do well in the class. Sure, you can do well in other ways. Yeah, you could go and find somebody who has taken every iteration of the problem and, like, get all of that information and then put it all together and take the exam at, like, 11:50 at night. But is that easier? No, I think that that's a lot of effort to, like, get all of that information from other people. That might even be harder than just learning the material, especially since that's only good for one exam, getting all the answers for this exam. You still have to do this again on the final. But if you learn it now, you'll know it for that. Is there any extra credit on the exam? Turns out the answer to that is yes. I offer 10% extra credit. So the exam's actually out of 83. But only 75 points are graded. So if you do extremely well on the exam, you can get over 100%. And I do that on the final too. The final's at 165 instead of 150. So exam time is your opportunity to show me that you have been preparing. On the quizzes, it's hard to do that because I can't really do 10.5 out of 10. Like, that doesn't really do much. But on the exams, there's enough points that I can do this. All right, so back to isotopes here. We talked about how on Tuesday that the identity of an atom was determined by the number of protons, and that for a neutral atom, the number of electrons was equal to that. And then we talked about ions, how you could change the number of electrons on that. We're going to talk more about ions in Chapter 9. But for now, in neutral atoms, these are going to have the same number of protons and electrons. But what about neutrons? A neutron has no positive or negative charge associated with it, so it's not going to create an electrostatic force. What that means is you could just put as many neutrons as you want in the nucleus, and everything will be fine, right? That's sort of true, but there are some constraints to it. So something I mentioned about neutrons is that you'll remember from a slide before that I talked about the strong nuclear force. The strong nuclear force works between neutrons and protons. And it holds everything together, and it's quite strong. But if the neutrons don't have any extra protons to hang on to, then the neutrons don't stick to the nucleus, in other words, and they just kind of decay and fall off. The other option that can happen is if there's just too many protons and not enough neutrons, in which case the protons repel, and the isotope that you have won't stick. So if you had something like, say, this, so let's suppose I had 10 protons and 5 neutrons. The symbol for a neutron is N with a 0 up here because they have no charge. This probably would not be stable. And the reason for that is there's just not enough neutrons. The protons would repel. I could do the same thing. I could have something like this. And this would probably be unstable also because the extra neutrons don't really have anything to stick to. Neutrons are attracted to protons, but when that proton-neutron attraction is shared amongst too many neutrons, then that interaction gets weaker and weaker and weaker the more that it has to split across. So somewhere in here will be a range of neutrons, so maybe like 8 to 13 neutrons. And that would work. And those are the possible combinations that will work. Yeah, so if protons don't stick, then they would be repelled by other protons. And what you would end up having is a nuclear reaction. Now, I'm sort of coming at this from the perspective of, hey, I have like a proton jug and a neutron jug, and I can just pour them in to whatever ratio I want. In reality, what's happening is somebody would have a nucleus of a certain size, and they would fire protons or neutrons at it and hope that they stick. And if they do, they would observe what happens. But the point of all this is that each of these different combinations of protons and neutrons is known as an isotope. And I ran out of space there. Let me try that again. Each of these possible combinations is known as an isotope. And specifically in this case, we're looking at the isotopes of whatever atom has 10 protons. So if you look at your periodic table, you'll find out that these are all isotopes of neon. Now, if you go to the internet and you type in Wikipedia, or just on Google here, I usually go isotopes of, and since we're talking about neon here, I'll type in neon here. And you know what I should do? Let me see if I can window capture this. Yeah, there we go. That's too big. So the first link here, Isotopes of Neon, leads you to this page, and it shows you every possible combination. Let me see if I can zoom this in here. Of Z, which is the number of protons, so these are all just going to be 10. And then N, capital N, is actually the number of neutrons. So they don't actually show Z and A on this page. But you can see here that neon with 5 neutrons and 10 protons lasts for about 7 times 10 to the minus 22 seconds. That's not very long. But if we give it 8 neutrons, it lasts for 1.6 seconds. If we give it 9 neutrons, it lasts 17 seconds. If we get 10 neutrons, it's stable forever. And so there's a range of certain combinations that are just stable forever. And then after that, like 13 neutrons last for 37 seconds. 14 lasts for 3.8 or 3.3 minutes. 15 is less than a second, and then so on and so forth. So, like, these are all different combinations of protons and neutrons for specifically neon. These are all the isotopes of neon. What we're going to care about for our purposes in this class are which isotopes are stable. So that's these guys right here. They're listed as stable. So neon 20, neon 21, and neon 22 are all stable. What we have here, these are the masses of these atoms in AMU. Don't worry about spin, because that's a physics topic. We're not going to talk about spin in this class. And then over here, we have, in this column, this is the percent abundance. What does it mean to be percent abundant? Well, that is describing that if you had a random sample of just neon, and you reached in and grabbed one, what's the probability that you grabbed a neon with 10 protons and 10 neutrons versus 10 protons and 11 neutrons, or 12 or whatever? And so this is saying that in a normal sample of neon that you would find on Earth, 90.48% is neon with 10 neutrons, 0.27% is neon with 11 neutrons, and 9.25% is neon with 12 neutrons. So that's how we identify isotopes, and then how we find information for them. And you can do this for any isotope you want. So isotopes of, let's suppose we wanted to do uranium. I don't know. Now I'm going to be on a list because I showed you guys this, but that's okay. Here are all the isotopes of uranium, and you can see that when you don't have enough neutrons, it doesn't last for very long, but then it gets longer and longer. Like this one is 68 years. This is like 10,000 years or 100,000 years, 200,000 years, millions of years, and then it just goes up and up and up, and then it starts going down again. So with uranium, the most abundant ones are 238, 235. I didn't actually know about 236. And how much of the uranium is 238 is 99.27% uranium-238. 235 is the interesting one because that's what's used in nuclear power. But there's not much of it. So we have to make it, which requires effort. Especially if you've played Factorio, you know that that requires effort. Where to buy smoke detectors in bulk? Well, now it's in the chat, and so those two things are going to connect together, and I'll expect the feds in any moment now. Alright, so that's how you look up isotopes. We're going to use this information. For the most part, I'm going to provide it for you on the slides, but in case you're like looking up stuff and you need to find it for a practice problem or whatever, that's how I generate that information. I go up and look it up. Alright, so let's look at boron here. These three isotopic notation symbols that I have written are all boron because they all have 5 protons. But you'll notice that the number of neutrons that they have is different. And I'm going to write this on the next slide, but how do you identify whether different species are isotopes of each other? The way that I instruct people to remember it is to remember same Z, different A. So if you look at two different atoms, and those different atoms have the same atomic number but different mass numbers, they're isotopes. What that means is that you can only be an isotope of a given element, and then you have to compare different atoms within that element. All right. Now, out there in nature, lots of different isotopes will occur, as we just saw on those charts. For neon, there are 3 different naturally occurring isotopes. What that means is that way back when the Big Bang, I mean literally way back, and all of the random subatomic particles came together and created matter slowly over time in the core of stars and stuff. The combinations that stuck around were the isotopes that we see today that are stable. Those are what are known as naturally occurring. All that naturally occurring means is that nature, quote unquote, made these isotopes and they stuck around. Because the age of the universe is very, 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 very long, anything that does not last longer than trillions of years will have gone away. It will have decayed. In the example that you saw on the uranium page, I still have it here. I could just put this back. Oops, where did it go? Let me grab it again. Yeah, there it is. Okay. On the uranium page, you could see that some of this stuff lasts for a long time. 4.4 billion years is a very long time for a sample of 100 grams of uranium to decay down to 50 grams. These are half-lives, and we won't really talk about half-lives in this class, but suffice it to say that a half-life of something is how long half of it will take to disappear and turn into other elements by falling apart. If you are looking at something on the scale of like planetary time, such as the age of the Earth, which is roughly in the billions of years old, then this stuff is still around for the most part. In fact, the uranium that is in the planet is a source of energy, more or less. So, like, the core of the planet is hot not just due to pressure and magnetism and things moving around, but also due to radioactive decay. And so all the uranium that is in the core of the Earth and is decaying provides energy in the form of heat, which is good because then, like, we have, like, volcanoes and stuff, I guess. I don't know. But other elements, for example, let's do this. Let's talk about technetium. Technetium has no stable isotopes. So if I go down this list, you'll find that the most stable one is roughly 42 minutes. Oh, no, there's some that are days. Here we go. Okay. Yeah, so this one is 61 days or so. Oh, no, there's some that have years here. So this one right here is about 4 million years. If you see the abbreviation A means annum, which is here. Since Earth is way longer than 4 million years old, and in fact, we've dug up, like, skeletal remains of dinosaurs and stuff from, like, 65 million years ago, this number is way too small. So what that means is that in a billion-year period, we've gone through thousands of half-lives. So the amount of technetium that's in the ground is essentially 0. So you won't find it. anything that has a half-life that is so short that we don't find it anymore is called synthetic. And yeah, that's more or less where I'm going with this. Wasn't technetium created before it was discovered? Technically, the answer to that is yes, because it's not discovered in nature. Its half-life is too short. So now you might have observed it, an atom of it, but nobody dug up a rock of technetium and was like, oh, this is an unobserved element before. They just observed, like, elements of technetium from random radioactive decay of other things. But technetium doesn't exist in nature. And the reason for that is because it's a synthetic isotope. Its half-life is just far too short. So the takeaway here is that if an isotope is naturally occurring, it's because it lasts a long time. Or in other words, it has a long half-life. But an isotope that's synthetic usually doesn't last long. And when I say long, what I mean is it's about hundreds of years or less, maybe even millions of years or less. So, relatively short half-life. And then there's half-life 3, which doesn't last at all. Ba-dum-bum. I'm glad somebody got that joke. Yeah, I've been told that that's actually a really good game. I don't have a VR setup, but I would like to try it at some point. Alright, so now that we've differentiated between naturally occurring and synthetic, we can talk about how to calculate masses on the periodic table. The periodic table only considers naturally occurring isotopes because they're what's available in nature. If you go to, I don't know, the element store, which of course doesn't exist, and you scoop into the bucket marked carbon, the only isotopes you're going to pull out of that are naturally occurring. You won't get any synthetic ones because they just don't last long enough. On this page, we have some ways of talking about isotopes. On the internet, you will actually see elements written like this. Carbon-14, iodine-131, cesium-128, stuff like that. When Fukushima, the nuclear reactor, had a meltdown, there were all sorts of things over the news talking about radioactive iodine. It's iodine-131, I believe. And so you might have seen that and wondered, like, well, what the heck does the 131 mean? The 131 is the mass number. So if you see an element written in this notation, carbon-12, or iodine-131, maybe it's 135, I don't actually know. 131 might be the stable one. What this is doing is it is just telling you the mass number without having to write a symbol. So these in yellow are much easier to format than this stuff up here, which is actually very difficult to format on a computer. So on an assessment like a quiz or an exam, and I don't think I actually have you do this type of problem on the quiz, but just in case you need to do it for the exam, you would just have to type out a name of an element, hit a dash for a hyphen, and then type in the number. And so using this notation, type in the chat what you would enter for something with 12 protons and 13 neutrons. And mass number is number of protons and neutrons added together, not electrons. So what would you call this atom that you have right here? Type it in the chat. While you are doing that, I'll talk about the potassium iodide pills. The reason that iodide pills are very useful in a radioactive situation is because, one, your thyroid, which requires iodine to regulate bodily functions, is easily saturated because it doesn't need much. In fact, if you eat any iodized table salt from like a salt shaker, you will get enough supplemental iodide that your thyroid should be okay. However, iodide is slow to be replaced. Its bioavailability is, or its bioactivity is slow. So if you consume something from a source that is radioactive iodine, then it will get in your thyroid and stay there and then possibly undergo radioactive decay. So what we do is we give you potassium iodide pellets or like dissolve them in this drink that you consume, which is really nasty tasting, is my understanding. What that does is it gives you so much iodide that it saturates your thyroid, and any additional iodine that you would consume is much less likely to be absorbed because you already have all the iodine that your thyroid can handle because you took the potassium iodide pill. So that's how isotopes can be useful. You know which isotopes are stable, which ones aren't, so you can use those in preparations such as with your thyroid. And everybody got the right answer. It is magnesium-25. So very good. Now, let's suppose I wrote it like this. How many neutrons are in this atom? So now you got to go find cerium on the periodic table and use this information to figure out the number of neutrons. So you got to work backwards. Tell me how many neutrons are in this atom. And don't look at the bottom number yet because we haven't quite gotten there. That won't help you, but the top number will. We got 81 as a guess. We got a bunch of people saying 81. Excellent. 81 is the answer. I don't know why I'm congratulating you if you have the answer on the slides in front of you, but maybe you did do the work. Please disregard any undeserved compliments. But if you did the work, you can keep them. So, all right. What happens if we have the same A but different Z? This is kind of a backwards trick sort of thing that has a different term. And if you're not careful when searching terms on the internet, you might accidentally get isobars instead of isotopes. Isobars have the same mass, but are different atoms. So, for example, if I had two atoms with mass number 60, such as cobalt-60 and nickel-60, they both have a number of protons and neutrons that equal 60 total. So they would weigh the same thing. What that means is I can't use physics to differentiate them. If I were to put atoms on a scale, they would weigh the same thing. But I can use chemistry because cobalt and nickel have different reactivities because they have different numbers of electrons. So isobars are particularly obnoxious when it comes to doing physical applications because we can't really isolate them physically. Isotopes are obnoxious because they're hard to separate chemically because they have the same chemistry. In these pairs below, where'd my cursor go? There it is. In these pairs below, what you want to do is look at the two and say, are they isotopes or are they isobars? So in this first pair right here, you'll notice that the top number, which is A, is the same, but the bottom number is different. That kind of looks like the word different, whatever. So these weigh the same thing, but they're different chemically speaking. So these would be isobars. For the second example, I have the same Z, but I have different A. So those are isotopes. And in this last example, everything is different. So they're just unique. They're iso nothing. They are different atoms, and they have different weights. We could distinguish them either using chemistry or physics. When I say chemistry, what I usually mean is we would do a chemical reaction. And when I say we can differentiate with physics, what I mean is you can weigh them and separate them that way. Oh, this one weighs more. It goes in bin A. This one weighs less. It goes in bin B. Yeah, something like that. So mass spectrometry, a centrifuge, things like that. Those are all used to differentiate between the masses of atoms. All right, so I've got some descriptions. Oops. I always think that there's going to be one more line at the bottom there. I've got some descriptions for you on the board here. What I want you to do is write the isotopic notation symbol for each of these pairs of atoms, X and Y. And I want you to tell me if they are isotopes, isobars, or neither description is appropriate. And we'll go over the answers in just a second. Type in the chat the... It's kind of hard to do isotopic notation in the chat, but just tell me, like, problem 1, these are iso whatever, and so on and so forth. We'll go over the answers just a bit, and then I'm going to go get more water. Be right back. All right, surprising absolutely nobody, I was ambushed by cats in the hallway, and everyone demanded a hug. So I had to go hug cats. Such a tragic life I lead. Oh, my cats are extremely needy. They demand hugs all the time. I don't think that this is normal for cats. Because most other people I see that their cats, like, they sit in their laps, and they'll do that for a long time. My cats want my attention for 5 minutes at most, every 20 minutes. Alright, so let's look at element number 1 here. So I have 3 protons and 5 neutrons, so that would be something like this. Which I believe is lithium, yeah. And then atom Y has 4 protons and 4 neutrons. 4 plus 4 is 8. Yeah, I love my cats too, but I also have to work. And I don't know if my boss would like seeing my performance evaluation that says, the lecturer talked about cats for 2 hours every week. Like, aren't you assigned to teach chemistry, Wes? Yeah, you know, but... Alright, so we got the same A, but different Z, so these must be isobars. Down here we have a carbon atom, so that's C with a 6 here. You'll probably notice that the number that you write for Z and the symbol are always linked together. For example, I could never write anything other than a 6 in front of carbon here, because it has to go that way. 7 neutrons, 6 plus 7 is 13. And then a nitrogen atom with 7 neutrons, so 7 plus 7 is 14. You'll notice that they have the same number of neutrons, but because they're different elements, they're just unique. Or unique, if you are 10-year-old me. Or 9-year-old me. I don't know. Maybe 5-year-old me. Whatever. I was growing up, I mispronounced words all the time. We have sodium 23, so here's sodium 23. And here's sodium 24. Those have the same Z, but different A. So they must be isotopes. That makes sense. That checks out. Unique. Alright, so that's isotopes, isobars, isonothing. Any questions? Let me know in the chat. How much time do we have left here before the break? We have a few minutes. I can probably start talking about what we're going to do for calculating isotopic mass. We more or less already talked about these. This is just me taking those charts that I showed you and putting carbon on the screen. So if we were to go to the chart for carbon, what you would find out is that carbon lasts forever. So if it is carbon 12 and carbon 13. Carbon 14 lasts about 5,700 years. And then carbon 15 is like 3 seconds at most. So if I go digging around in the carbon bin, and by carbon bin what I mean is either diamond or charcoal or graphite. They're basically the main places carbon ends up. Those carbon sources have come from the ground. For the most part, like 99.999% of charcoal comes from the ground. It's just been there. It's in the earth. If I were to analyze that with a mass spectrometer and decide, or not decide, but determine what was in there, I would find these because it's stable. If the carbon was produced within the last 5,000 to 10,000 or so years, I would absolutely find this. But if it was longer than that, I might not. And there's absolutely no way I will find any of this. Because it just doesn't last long enough. So carbon 12 and carbon 13 are naturally occurring. Carbon 14 is also naturally occurring because it lasts long enough for us to see it. And somebody mentioned in the chat carbon 14 dating, and that's actually where we're going with this. And that is how much carbon 14 is available in the environment, and how can we use this to our advantage. And as an aside, if I talk about carbon 14 dating, the way that this works, I guess we could draw a picture of this if you were curious. So let's suppose that I am a dinosaur. Oops, that's not the pen. All right, so here's me. All right, so I'm this dinosaur. And I am an herbivore, which means that I like to eat leafy green things. So here's my leafy green thing. I like that my dinosaur is a more realistic drawing than the leafy green thing. But that's okay. Inside my leafy green thing is carbon-14. And there is some small percentage of it. We'll say like... I think it's like 0.1%, I want to say, but I'm not sure. Now, if I have been eating these leafy green things all my life, what that means is that the carbon that is incorporated into me, the dinosaur, will also be about 1% carbon-14. Or 0.1%, sorry. Now, carbon-14 doesn't last forever. It lasts about 6,000 years or so. What that means is that if I know what the mass of carbon is in the dinosaur, then I could say that 0.1% of the mass of carbon is carbon-14. However, because carbon-14 is radioactive, you would have to constantly be replenishing it. Well, what happens when you die? You stop eating, right? So if you are no longer alive, and so here's my dinosaur who's dead. He's no longer eating this. And so no more carbon is passing through his body to replace the carbon-14 that was lost. And so what that means is that after death, the amount of carbon-14 in the dinosaur's body will slowly decay over time. And so, if there was this much carbon-14 in the dinosaur at that point, there will be less and less and less and less and less and less over time. Well, you can model an equation to this. And it's something like this. And if you know the amount of carbon-14 in there, you can figure out how many years have passed since the creature was alive. And this is called carbon-14 dating. And you won't be tested on that. That was me basically trying to use up 5 minutes so that I can take a break on the correct time before starting a new topic. But this is how carbon-14 dating works. It is based on the premise that there is a constant amount of stuff in the environment that then becomes a part of the organism. And once the organism stops incorporating that isotope into their diet because they've died or it was harvested or whatever, you can measure how long ago something was killed. You can do this with trees and wood, for example. I think there's a practice problem that talks about a wine bottle that the cork was submitted for carbon-14 dating, and so someone claims that it was like from Leonardo da Vinci's basement. And when you do the carbon-14 dating and you find out that the amount of carbon-14 in it is only enough for it to be 200 years old, so it came from like 18th century Italy instead. So you can use that as pretty conclusive proof that, like, hey, this is not within the correct time frame. And they've done this with a bunch of things. So I think that they did this with the... Oh, goodness. I forget what the shroud is called, but it's the one that they put over Jesus, presumably. And I say presumably because when they carbon dated it, I want to say that the time it was well after 0 AD or 1 AD. When they dated that. So it was like, oh, this was made too recently. So you have evidence that this material is not actually what it claims to be. You could do this with like paper and parchment and stuff like that and figure out, oh, this was written in roughly this time. Now, is it perfect? It's not, because there's always going to be some natural variance with the equation and also the amount of matter that something consumed. If it's something big like a dinosaur, you're less likely to have variance because they're very large creatures and you have more material to work with. So you're more likely to get a regular sample. But something really, really, really small, if you used its entirety, you're still pretty likely to get a good sample because the number of atoms is relatively large, but the potential for error does exist. How do we know it had 0.1% carbon-14 when it was alive? We are sort of working on the assumption that the amount of carbon present at that time is the same as it is now, because the half-life of something is independent of time. Like, it will always last for X amount of years. But barring any sort of strange process which suddenly created an abundance of carbon-14, so like maybe a year of solar flares, like, I don't know. It's extremely unlikely that there would be more carbon-14 than would be typical. So what we're basically doing is saying there is 0.1% carbon-14 now. There must be 0.1% carbon-14 then. Volcanic eruptions are pretty unlikely to change the amount of carbon-14 because that carbon is already, well, it's hard to say. I'm sort of going off the beaten path here. The way that carbon-14 comes about usually is from solar radiation. So you get something with like carbon-13 and it absorbs a neutron from the sun. Like the sun is just spewing particles out of it. And it's called solar wind, and you can look that up if you'd like. But some of those particles include things like neutrons, and so a neutron could be absorbed by a carbon-13 nucleus to become a carbon-14. But there's only so much carbon in the atmosphere and on the ground, and that actually the neutrons that make it through the atmosphere can get to. And so the average equilibrium over time ends up being about 0.1% of carbon. That's my best explanation of it. I'm not sure if that's entirely correct, but it's what I sort of remember. I'll have to look it up during the break. So we're going to take a break now. Let me put the break time card up here. Oh, I don't have a timer. I never have the timer ready. I gotta find more Persona music here real quick. So let me, where's my window? There we go. So we'll go to Persona 3. And we'll put this on here. All right. See you in a bit.
awake and repeats loud, face reality, never be charity. The enemy you're fighting covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then on your rival. Round up around, spit out, all over. Rhyme like a rolling stone, calm in the crowd. Watch out the moon, they diss too loud. Guess what this sound and bombs whole ground. So round up, don't ease your case, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one love. But the battle goes on, shadows all mass destruction.
Oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down, da-da-da-down. Oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down. Oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down, da-da-da-down. Oh yeah, da-da-da-down, da-da-da-down. Baby, baby,
Feels awake and breathes loud, face reality, never be charity. The enemy you're fighting covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then on your rival. Round up around, spit out, all over. Rhyme like a rolling stone, calm in the crowd. Watch out the moon, they diss too loud. Guess what this sound and bombs whole ground. So round up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one love. But the battle goes on, shadows all mass destruction.
oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down, da-da-da-down. Oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down. Oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down, da-da-da-down. Oh yeah, da-da-da-down, da-da-da-down. Baby, baby, da-da-da-down.
All right, hi everybody. We are back. Just sitting here geeking out about Persona 3 because I enjoy it. If you haven't played the Persona games, and you want to relive what it's like to be a high schooler in Japan, they're great. Maya thinks so too, huh? Maya is actually named after a character from Persona 2. So, say hi, Maya. She's literally right here. She's trying to climb onto my lap. She probably will do that during the lecture here. Okay, so we've talked about digging up random samples of carbon in like a block of charcoal or whatever. And that we would have definitely carbon 12 and carbon 13 in there. We'd have a little carbon 14, but we wouldn't have carbon 15. We've already talked about half-life. We'll talk about it more in Chem 163 when we actually calculate it. Oh, there goes Maya. Okay. What we are going to talk about today is how to calculate percent abundance from numbers on the periodic table and numbers that you can look up, or how to calculate masses or atomic mass. So here's how this works. If I give you a percentage of one of the two isotopes that are naturally occurring, the other one must be whatever is left over. So if carbon 12 is 98.89% abundant, then whatever is left must be the difference, right? So 1.11. Now, this is exactly 100% up here. So whatever degree of precision I get for my percentage, I can then use that for my other number. Okay? So obviously that makes sense, right? Because that's how percents work. This is some percent of the thing, so the rest of it must be the other thing. Now, if I have two species where I have X% of one and Y% of the other, then I know that X% and Y% added together must equal 100%. You might think, well, duh, why do we need to make algebra out of it? Because that's going to be extremely important to us later. Okay? Now, what we're going to eventually do is we're going to change these from percents into decimals, which means that I just divide everything by 100. Well, 100% actually. And then I'll get this. That's going to be crucial. So we're going to come back to that in just a second. All right. I'm going to erase just to put this on the screen. There's nothing really new here. We've already talked about how long isotopes last. Okay. We're going to come back to that concept of isotopic abundance, and we're going to combine it with the concept of how we weigh atoms. Now, 161 starts off with a little bit of discussion on mass spectrometry. And we have determined that the mass of a carbon-12 atom using this technique is this amount. That's really small, so we're going to change that unit to something that's more convenient. We're going to take this number, and I'm going to write it as... Oops, no, that's not the right number. Sorry. Those are different things, because this is 12 proton, or mass number 12. We're going to take this number and convert it into this different unit down here called the atomic mass unit. The atomic mass unit says, okay, I'm going to take a proton that weighs this much, which is really tiny. I'm going to call it this, which for our purposes is essentially 1 AMU. The same is true for a neutron. This is what a neutron weighs. And then an electron weighs this much, so it must weigh this many AMU. So the short version of this chart is going to be that a proton and a neutron are approximately 1 AMU each, and an electron is going to be nothing. So this unit lets us assign a mass that is roughly the number of protons and neutrons in the atom, and then just tack this unit at the end, AMU. We can ignore electrons because electrons are so light relative to the nucleus of the atom. We would need thousands of electrons to contribute the mass of one hydrogen atom. And no atom has 1,000 electrons. So if we're working with small molecules, we'll never have to worry about the influence of electrons because it'll get lost in the sig figs. The mass of the electrons will not be large enough of a contributing factor for us to care. So we're going to work with this unit, AMU, because it's easier for us to conceptualize a number that is roughly 1 to 100, as opposed to a number that is roughly 10 to the minus 23. So if I report the mass of an oxygen atom as 16.01 AMU, what that means is that, oh, it has a mass number of about 16. The mass number will always be rounded to the AMU mass of the atom to the ones place. Now, there may be other decimals that we can get, and we're going to keep those decimals that are shown here. Oops, I lost my cursor again. We're going to keep these decimals when I give you the masses of elements and stuff like that, just to have more sig figs. But if you just eyeball it and look at something and say, okay, this aluminum atom has a mass of 26 AMU, does that check out? And you look at the periodic table and you see 26.982, and you think, oh, maybe it should be 27. And then you can, like, make an informed decision. Or maybe you are looking at aluminum 26, or whatever. Alright, so that's a discussion about mass. Let's put those two things together and start figuring out how to weigh everything else. And get the mass of stuff on average here. I'm going to talk about this slide in more detail next quarter, in 161. But suffice it to say, using the mass spec, we can weigh other atoms, and so we will get these masses that are on the Google or Wikipedia pages that I showed you earlier. Alright, here's where we put it all together. I'll put the formula on the board in just a second. So, the first mass that we're going to define is the isotopic mass. The isotopic mass is the mass of a single individual isotope. Every isotope has an isotopic mass. And it will be roughly the same as the number, or its mass number. So if I take this is boron 10, so it should weigh about 10 AMU, and it does. And this will always be true. You will always round to the mass number for that specific isotope. If I were to look up boron 11, it might weigh 11.011 AMU, or something like that. Generally speaking, elements that weigh more than carbon-12 are just a little bit less than what you'd expect them to be in AMU, and elements that are lighter than carbon-12, such as boron 10 here, are a little bit more than what you'd expect them to be. This is due to relativity and how fusion works. When you combine two protons together from two hydrogen atoms to get helium and put a neutron in there, you actually lose a little bit of mass in the exchange for energy. This is called fusion. This is how the sun works. It's beyond the scope of this class, but the masses don't exactly add up. You get a mass defect. Not mass effect, that's a game, but mass defect is the difference in mass which is converted to energy using E equals mc squared. There's a lot of really cool physics stuff out here, by the way, that we're not going to go into. Alright. Now, if I take all the isotopic masses of all the elements... Oops, that's the wrong color. If I take all the isotopic masses of all the different isotopes that are naturally occurring. Oh, I'm gonna sneeze. Hold on, let me hit mute. Now I've done it, I can't sneeze. I'll probably be okay. I'll leave the mouse over there. Oh, it's gonna pop back over here once I put the cursor on the screen. If I take all the isotopic masses of all the naturally occurring isotopes, then what I do is I take the average of those masses based on how many of them we find. Now, this is what's called a weighted average. In order to talk about weighted averages, we have to first talk about regular averages. So we're going to do that on this screen here. Oh, I should probably clear my dinosaur. Oops, I don't know why that happened. So there we go. If I want to take the average of two numbers, say these two, what you would do is you would add them together and then divide by the number of numbers that you did, right? Now, this is just sort of a formula that we've given you in algebra, but in reality, this is what you're doing instead. Right? All I did was distribute the half out, right? And so what these are right here are called weights. And because I am equally weighting both contributions, so the 6 and the 8 are equal contributors, they affect my average by half each. Now, if I had 3 numbers, I would have the same thing going on where it was like this. And then I would do this. And my cat has decided to use my chair as a scratching post. What are you doing? Hi. I'm working. He's meowing at me. Same thing, right? So I would have equal weights. Now, let's suppose that you're in a situation where you don't have equal weights. Maybe you had a bag full of marbles that weighed 6 pounds, or 6 pounds. Like, each marble either weighed 6 grams or 8 grams. If you had equal numbers and you just grabbed marbles randomly, the average mass of each marble would be 7 grams. But let's suppose that they weren't equal. If instead you had 90% of your marbles weighed 6 grams and 10% of them weighed 8 grams, then what would the mass be? And if I type that in the calculator, I get this. And so what that means is that this is the average if these are my weights, or in other words, the weighted average. If I have more of one thing, the average gets skewed towards that thing. So let's suppose that I had 2 different atoms. I had iron. I gotta look at the periodic table here. 55 and iron 56. Oh, he wants attention right now. He's not gonna get it. I don't know if you can hear him meowing at me. Now, on the periodic table, it says that the weighted average is 55.845. What does that tell you that there is more of? Is there more iron 55 or more iron 56? What do you think? If the average is 55.845, then the iron 56 must be tilting the average more towards it, right? So there must be more iron 56 in the mixture. And that's exactly right. Iron 56 is more abundant than iron 55. Otherwise, the weight would be skewed towards iron 55. So this is the premise behind how we're going to calculate weights, is that by adding all of these individual masses of isotopes and their abundance, and doing that for each species, we'll get the average mass. And the average mass is what goes on the periodic table. So let's go back to the slides and we'll put the formula on the screen here for what is happening. So you saw me use this formula on the next slide. This formula expands forever. You can use it for as many terms as you have isotopes. Generally speaking, we're going to do between 2 and 3. In theory, you could use it for 20. You could use it for 1,000. It would just get really tedious to do that. In the spaces marked mass 1, mass 2, or whatever, these are isotopic masses. In fact, you know what I should do? Let me do it this way. So these are isotopic masses. The percents that are shown here are the natural abundance. So like that. Importantly, we want to write that as a decimal for the equation to work. And then finally, the atomic mass that is shown, that's the wrong tool. The atomic mass shown here is the average mass that is shown on the periodic table. I mean, you could shorthand it however you want to. I just would not... Canvas would not recognize it if you had to type that word, and I don't think anybody else outside this classroom would. All right. We're going to use that formula to figure out the numbers on the periodic table. And then what we're going to do is we're going to do different problems where we start solving for different things. Okay? So we're going to use this formula for the rest of what we're going to do today. All right. Let's do an example. So here's boron from the periodic table. And what I want to do... I want to calculate the atomic mass based on these numbers. So let's go to here. That's kind of blank. There we go. And so what we want to do is we want to calculate the atomic mass of boron, which is already shown. But we want to show that with the information that's available on the internet, we can get that. Okay? So we have the abundance percentages, which I looked up on Wikipedia. And we have the isotopic masses, which I also looked up. So we're going to write down the formula. So that is the atomic mass equals the percent of the first isotope. So I'm going to call that percent of isotope 10 times the mass of isotope 10 percent of isotope 11 times the mass of isotope 11. And you can do whatever shorthand you want for this. I'm just putting all the algebra down before I do the numbers. So what percentage of 10 do we have? We have 19.9%. So I want to write that as a decimal. Times its mass 10.0129 AMU. Plus the percentage of boron 11, which is 80.1. As a decimal, that's 0.801. Times 11.0093 AMU. Now I'm doing a multiplication, and then I'm doing an addition. So I got to worry about sig figs here, which means that when I multiply these two numbers together, the result's only going to have 3 sig figs, yeah? Same thing here. Oh, here comes that sneeze from earlier. Hold on. No, never mind. Every time I think I'm going to sneeze, I think, oh, I'll just talk about it, so you know that why I'm muting for 5 seconds. But all right, I'm punching this in the calculator. 0.199 times 10.0129, and I get this: 1.99 AMU. And then I'll do the same thing to the other one: 0.801 times 11.0093, and I get 8.82. Now I have an addition. Since it's addition, I'm going to go to the place that both have a sig fig in, which is the hundredths place. So if I do 8.82 plus 1.99, I get 10.81 AMU. Oops. There we go. All right, so this is the average mass of all the naturally occurring isotopes, or its atomic mass. How did we do on the table? Well, I got 10.81. Periodic table says 10.811. That's pretty darn close. And the only reason that we weren't closer is because we just didn't have enough sig figs based on the percentages that were available. How many sig figs should your answer have? Well, it's always going to just depend on how the math works out. So don't look at this and say, oh, there were 3. I should have 3, because it turns out we needed more than that based on the operations that we did. All right. That's a simple one. Let's do a slightly more complicated one. Here's chlorine. For this example, I have given you the masses. And here is the mass of chlorine on average, its atomic mass. What is the percent abundance for each isotope? Uh-oh, I got to solve for the percentages. That's a little bit harder. Here's how we do it. So I definitely want that on the screen. There we go. Okay. So I'm going to leave the formula here, but I'm going to delete everything else. Well, if I could select everything else. There we go. Boop. All right. Now, this isn't going to be boron 10 and boron 11 there. But what we can do is we can say, okay, if this is chlorine 35 and this is chlorine 37, the formula should still be the same, right? Now this is chlorine, so I know this number. I know the mass of isotope 35 and I know the mass of isotope 37. But where I get stuck is that I don't know these percentages, right? And you might think, uh-oh, I have one equation but 2 unknowns. How the heck do I solve it? And the answer is, well, remember before, we said that if there are two isotopes, they have to add together to 100%, right? So now I have two equations and two unknowns, and that's solvable. How many of you thought that in Chem 140, you were going to have to do something like this? And solve this system of equations. Guess what we're doing right now? We are doing exactly that. So even though it looks like all the algebra that you were covering in your math classes is completely useless, sometimes it's not. So when you have a system of two equations, how do you solve it? Like, what's the first step? And if it makes it easier for you to do something like this, x, y, x, y. Yeah, you substitute, right? So let's do that. So if x plus y equals 1, I can just say that y is going to be 1 minus x, yeah? And then I can take that and I can just put it in wherever I see y. So let's do that. So I have the atomic mass of Cl is going to be the percent of chlorine 35, which we called X, times the mass of chlorine 35, which is a number we know, plus the percent of chlorine 37, which is Y, which we have substituted as 1 minus X, times the mass of chlorine 37. Now I have one, so remember, I know what this is, I know what this is, and I know what this is. I now have one equation with one variable. I can now solve this. So we had to do some algebra, which means that I'm going to just call this mass of chlorine equals M35 times X. I have to FOIL this out. So this would be M37 minus M37 times X. I'm just doing this plus this minus that, so I no longer need these parentheses. I gotta get X by itself, which means that I need to get all of the numbers that have an X on one side. So these guys should stay on this side, but this one's gotta go over there. Oops. Now that I have this part of my equation, I can then factor out this X here. And now I just divide both sides by this part, and it's done. So this relationship here should be the percentage of chlorine 35, which we have called X. And so let's do that. Let's fill in all the numbers based on what we know. So the first number was mass of chlorine, 35,453 AMU. The second number was the mass of chlorine 37, 36.9659. Now, don't worry that that's going to be a negative, because you might think, well, how can I have negative percent? And the answer is you can't. But if the top number is negative, and we've done the algebra correctly, the bottom number could be negative 2. And you'll notice that it actually is, because this is 30... Oops, not 35. 34.9689 AMU. Minus 36.9659 AMU. For the love of Thor, do not cancel these. This is subtraction. You cannot cancel these two numbers out. You have to do the subtraction on the top and the bottom. So I'm going to do this subtraction using my calculator. Notice that this number is only going to the thousandths place, while this goes to the 10,000th place. So we're actually going to chop that calculation off right there. And I get negative 1.513 AMU. I'm going to do the same thing for the bottom, but these both go to the thousandths place. Or sorry, 10,000ths place. So I get to keep all those numbers. 34.9689 minus 36.9659. I get negative 1.9970 AMU. And then finally, I just take this number and divide it by this number. And when you're done, you should get 0.7576 for the amount of the percent amount of isotope chlorine 35. So if X is equal to 0.7576, then Y must be 1 minus X, which would be 0.2424. And so there you go. So if the isotopic mass of chlorine, if the atomic mass of chlorine is 35.453, and there are only two isotopes, 35 and 37, this must be their distribution. Yeah, you can multiply these by 100%. So it would be 24.24% and 75.76%. And so I'm actually using real numbers to do this. We'll go back to this slide and I'll just hit the space bar to put the percentages up. I only wrote 2 sig figs, probably because I solved it the other way when I did it on paper. But if we go to isotopes of chlorine, my tab is closed or sleeping here. And you look up what the percentages are, you'll see that. Oops, you can't see that because that's too tiny, but you'll see that our percentages that we got here, 75.76 and 24.24, pretty darn close to what we calculated. All right. Now, there is something to note here. Depending on what you substitute for, you may get a different number of sig figs. What that means is that in this example right here, where I did all of this, I substituted y, and that was my answer. But I could have done x equals 1 minus y, put that in for x, and then solve for y. If I do that, I get a different equation and a different result at the end, and I could get a different number of sig figs. Okay, so be mindful that when you are doing this, depending on which operation you choose to substitute for, you could potentially get one more or fewer sig fig. That's typically an issue that comes up if one of the isotopes is much, much, much smaller in terms of abundance. So like 99% and 1%. For the purposes of Canvas, I always tell you the number of sig figs to put in for most of these problems. So I guess I can't say I always do it. Usually I will tell you the number of sig figs you need. For these, I will say enter your answer to 2 decimal places or whatever. And just make sure you were doing sig figs correctly all the way up to that to make sure that you don't end up having a rounding error at the end. All right, so we got 20 minutes left, which means that I have a problem for you to try. I have two of them, actually. So what I want you to do is for this first problem up here, I want you to tell me the atomic mass of silicon based on these numbers, and then compare it to the periodic table. Put in the correct number of sig figs that you get from your calculation. And then down here at the bottom, I have this fictitious element that I made up, element X. Here's what its atomic masses are. Or I'm sorry, here's what its isotopic masses are. If this is the average atomic mass, determine its percent natural abundance, okay? So try these. I'm going to figure out why my cat is screaming. He just wants hugs, you guys. And I'll be back to help you guys with the answers in about 6 or so minutes. All right, we have some answers coming in. How much time do I have left? I should probably go over the answers here just to make sure that we get them out in time before class ends. So, all right, so let's do the first one. So we've got 28 silicon. 29. Oh, I don't want to actually do that. All right, so we've got the average mass, the atomic mass is equal to the percent abundance of silica 28 times the mass of silica 28 Same thing for silica 29 and silica 30. And now there's another different cat here. Yes, I hear you. Oh my goodness. Okay. This is why I cannot have more than 2 cats. I would go crazy. I'm already going crazy. 0.9223 times the mass of 28, which is 27.9769. We'll do the same thing over here. 0.046858 times 28.9765. And then the third one, 0.030921 times 29.9738. There you go. So now we just got to add all of these up. That's not a calculator, that's my phone. And so let's do these to the correct number of sig figs, of course. So this first edition I got should have 5 sig figs, so I have 25.801 AMU. For this second one, I got 5 sig figs, so 1.3578. And then for the third one, is also 5 sig figs, so 0.92682. So I got thousandths place, 10,000ths place, 100,000ths place. Means I'm going to go to the third decimal place on all of these. 0.801, 1.3578. And I got 28.08562. So I should report that. How close did we get on the periodic table? I think they match exactly. That's pretty good. All right, so hopefully that's what you got. Now, it looks like people did. If you did, Maya is very happy for you. Huh, Maya? Maya, say hi. Meow. No, she won't say anything. All right, let's do the last problem. Now, unfortunately, there isn't a formula to really go through these types of problems when you solve for a percentage. You sort of have to do it every time. So the atomic mass of element X will be the percent of isotope 70 times the mass of isotope 70 plus the percent of isotope 73 times the mass of isotope 73. And we know that the percent of 70 and the percent of 73 have to add together to equal 100%. Let's just do the substitution right away. So I'm going to solve for, well, let's solve for X this time. It's functionally the same thing. You can do it however you want to. So I'm going to take this and put it right here. So that's going to give me the mass of X is going to be 1 minus Y times isotope 70's mass. So then I can FOIL that out. And once I've got that, I don't need these parentheses anymore. I can then isolate all the terms without a Y on the left and isolate all the terms with a Y on the right. I'm going to rearrange this a little bit. So mx minus m70 equals, I'm going to just flip these two. I can then factor out my Y. And then I can just say Y equals everything else after dividing. And so that's going to be, what was the mass of element X? So according to the problem, it was 71.225 AMU. And we've got M70, which is 69.938 AMU, divided by M73, which is 73.014, minus M70, which was 69.938 AMU. I haven't been canceling out the AMUs today, but they do all cancel out. When I do the calculation on the top, 71.225 minus 69.938, I get 1.287 AMU, which will cancel out on the bottom. When I do the calculation on the bottom, I get 3.076. And so Y is just 1.287 divided by 3.076. Or 0.4184. And so X just must be whatever 1 minus that is, or 58.16%. So we can take all this information and we'll put it in this giant box up here. We could say that the percent of 70 and the percent of 73. So we said that the percent of 70 was X and the percent of 73 was Y. So X was 58.16% and Y was 41.84%. And so hopefully that was what you got when you did the calculation. If you went in the other direction and solved for X instead of Y, you might get a different number of sig figs, but the process is more or less identical. You will get the same number at the end. Finally, you can check this by putting it back into the calculation. So if you aren't sure if you have the right number, try putting it in the equation. So you could type in 0.5816 for the percent of X times the mass of X, 69.938, and adding the other abundance, which was 0.4184 times its mass of 73.014. And if you hit enter and it equals the number on the screen, I got 71.225, which is actually kind of off. I'm not sure what happened. I might have messed up a number when I was writing or putting it on the screen here. That's close enough. So I was good down to 3 sig figs, but I'm off very slightly. So I might have switched 2 numbers when I was writing them down or copying them off the calculator. What numbers did you get for X and Y here? Oh, I see a problem already, so. Here's my problem. I wrote a 2 right here. This should be a 5. So let me see how that changes it, because that could be pretty significant. 255 minus 69.938. This is why you check your answer, right? So now the top up here is... Oh, that's not what I wanted. So I got that. Let me double check that the bottom is the correct number here. $3.76, okay. So 1.317. Almost did it again. I almost hit the wrong number. So now I have 42.81. Oh, no, the last one was 2. And then this will be 1 minus answer, 57.18. So we could fix this up here. I'll just do this. But yeah, this is why it's good to check your answer. Before you punch it into Canvas and hit submit. There you go. And it took us like, what, 2 minutes to do that? There you go. Now my answer seems to match what yours is. All right. Fortunately, when I'm programming the key into it, because like what I have to do is I have to type this equation into Canvas. This is what I tell it to do. Like I have to write out the algebra on paper and then tell it the variables. I'm not punching numbers into Canvas. I'm punching variables. And if I make a typo on the variables, one of 2 things will happen. The answers become ridiculous, and I immediately see, like, oh, you can't have negative 74%. Or it tells me I have a syntax error, and then I have to go back and fix it anyway. So Canvas won't mess up on this when I'm programming it, which is good, because otherwise, if I had to punch in all of these numbers individually, it'd be very difficult. All right. I think that that's it for Chapter 7. I guess we won't get to Chapter 8 today because class is over, obviously. But that's it. Hooray. Okay, so what that means is that there is a quiz for Unit 7 and 8. You have an exam on Monday, which is also going to have content from Unit 7 and 8. So the quiz for this week is only going to be open for about 3 days. So it's going to be open on Thursday once we do Chapter 8. Actually, you know what I'm going to do? Tomorrow's just a Q&A, right? I'll send out an announcement for this. What we'll do tomorrow is instead of having the Q&A, I'll do the lecture for chapter 8 because it's really short. It's going to take like 20 minutes. And then we'll do the Q&A, and then Thursday can just be review for the exam. But if I do that, then what will happen is I can open the quiz on Wednesday, and you'll have it open until Wednesday, Thursday, Friday. It'll be due Friday night for the soft deadline. I'll make the hard deadline Sunday. And then the answers will be open all of Sunday for you to look at them if you want to. And then the exam is on Monday. So that probably works out better. Okay? So that'll be the agenda for this week. I will make an announcement right now because otherwise I will forget. But plan to come back tomorrow. We'll do chapter 8, and then we'll do the Q&A like we normally do. And then Thursday's just a review day. We're actually pretty ahead of the content where I wanted to be. For a review day to work, you got to bring me questions, so make sure you have them. Otherwise, we're just going to do worksheet problems or homework problems or whatever. More or less what we're going to be doing on the rest of Wednesday. Okay? So we'll put this up here and call it a day. Thanks for coming out to the lecture. I hope... there's one last question. Is the exam on Monday only? Yes, the exam's open only on Monday. But if you're in a circumstance where like you really need it open on Sunday instead, I can only have it open per student for a 24-hour block, but I can move that block individually for students if you provide a reason for that over email. So like email me and say, hey, I work on Monday. Is there any way I can take it on Sunday? Yeah, I could do that. Okay. I just need a record of it in my email box so I know, okay, this student needed me to move it. Okay. Something like that. Anyway, thanks for watching, and I will see you all tomorrow for Chapter 8. Have a wonderful evening, and stay warm out there, because it's starting to get chilly.